In this video we are going to consider the motion of a particle which is moving in a vertical circle. Now we have seen that for general motion in a circle of radius r, the speed at any stage is just the radius times by the angular velocity, so that's the radius times by d theta by dt, or we can write this as being r times theta dot. We've also seen that there's an acceleration of magnitude r times the angular velocity squared, or v squared over r, towards the centre of the circle, and there is a tangential acceleration as well. For all the questions that we're going to be looking at, the circle is going to be vertical, and we're going to start the solution by applying the conservation of energy. Now, to apply the conservation of energy, we are certainly going to need to assume that there is no air resistance acting on the particle. Having applied the conservation of energy, we will then apply Newton's second law towards the centre of the circle, and if necessary we'll apply Newton's second law tangentially, although in WJEC examples this is highly unlikely to be necessary. So let's now have a look at our first example. We have a light rod OA of length 2 meters, which is fixed at the point O and free to move in a vertical plane about the point O. A particle of mass 0.4 kilograms is attached to A. Initially the particle is held with A immediately below O, and is then given an impulse so that the particle initially moves horizontally to the right with speed u meters per second. We've got to describe the subsequent motion of the system in each of the cases: u equals 5, u equals 8, and u equals 10. Now, if the particle is only given a small impulse, so that u is small, then it's likely that the particle will just simply swing to and fro about the lowest point. On the other hand, if it's given a really large impulse, then it's likely that the particle and the rod will manage to go round in complete circles about the point O. So we need to convince ourselves first of all that the particle will either go round and round the circle without ever stopping, if it's been given a large impulse at the beginning, or it will come to a stop at some point and reverse its direction and will keep swinging to and fro about the lowest point. So let's have some diagrams now. So here's the diagram showing the initial position of the particle, with the particle having been given an impulse so that it's got its initial velocity of speed u horizontally. And here is the position of the particle at some later stage whilst it's still moving, and it has moved through an angle theta from its initial position. Now we're going to apply the conservation of energy to the problem, and we can apply the conservation of energy since the only forces acting on the particle are its weight, and the work done by the weight is always looked after by the potential energy term when we apply the conservation of energy. And the only other force that we've got is the tension, or possibly the thrust, in the rod. Now the tension or thrust in the rod is perpendicular to the motion at every instant, and therefore it does no work, because a force that is perpendicular to the motion does no work. So, if we're going to apply the conservation of energy, we need to introduce a zero potential energy level. The bottom of the circle will thus make all the potential energy terms positive as we go through the question. And to apply the conservation of energy, we need an expression for the height above the potential energy level of A, or of the particle, when it's in this general position. And we can do that by just saying that we're trying to find this height h here. And if we form a little right-angled triangle formed by O, the present position of A, and the vertical, then we can see that the height, the A is a distance 2 cos theta below O. We know that the bottom of the circle is 2 meters below O, and therefore h is 2 minus 2 cos theta. We're now in a position where we can apply the conservation of energy. So there are my two diagrams again. Applying the conservation of energy then, we have the initial kinetic energy plus the initial potential energy is going to equal the final kinetic energy plus the final potential energy. Now initially the kinetic energy is a half mu squared and the initial potential energy is 0. So the initial Ke plus the initial Pe is a half mu squared plus 0, but we know that the mass of the particle is 0.4 kilograms. So we've got a half times 0.4 times u squared as the Ke term plus 0 as the Pe term. Moving to the second diagram, the Ke in this case is a half times the mass 0.4 times v squared plus m 0.4 times g times h. So tidying this up a little bit, we've got 0.2 as a common factor all the way across. So if we divide through by 0.2, we get u squared equals v squared plus 2gh. Rearranging this to make v squared the subject to the formula, we obtain v squared equals u squared minus 2gh, or v squared equals u squared minus 19.6 times by 2 minus 2 cos theta. Multiplying out the brackets gives me v squared equals u squared minus 39.2 plus 39.2 cos theta. And this equation that comes from the conservation of energy is going to tell us a lot about the subsequent motion of the particle. So, if the particle stops, then v must equal 0 for some value of theta. So that means that we've got 0, or v squared, must equal u squared minus 39.2 plus 39.2 cos theta. Rearranging that, we've got 39.2 minus u squared must equal 39.2 cos theta, or equivalently, we've got cos theta must be 1 minus u squared divided by 39.2. So, if we take the case when u equals 5, then v equals 0 leads me to the equation cos theta equals 1 minus 25 over 39.2. In other words, I've got cos theta equals 0.362, which gives me theta equals 68.8 degrees. So in this case, the particle comes to a halt when theta equals 68.8 degrees, and then clearly will just fall back round the circle to a position where theta equals minus 68.8 degrees, and it will simply swing to and fro between theta equals minus 68.8 degrees and theta equals 68.8 degrees. If instead we have u equals 8, then our equation for v equals 0 becomes cos theta equals 1 minus 8 squared divided by 39.2. In other words, cos theta equals minus 0.632. And this has a solution of theta equals 129.2 degrees. So again, in this case, the particle is going to be oscillating or swinging from one angle through and then back again, but in this case the particle is moving on the circle but only between theta equals minus 129.2 degrees and theta equals 129.2 degrees, and it's going to and fro between those two angles. On the other hand, if we have u equals 10, then the equation for v equals 0 gives me cos theta equals minus 1.55. And we know that's impossible because cos theta can only take values between minus 1 and plus 1. So cos theta equals minus 1.55 is impossible. That's telling me that v is never equal to 0, which means in this case that the particle is going to complete full circuits of the circle without ever stopping. Now we're going to make a small change to the example. We're going to replace the rod by a light string of the same length. Now the difference between a string and a rod is fairly obvious. A rod is rigid, it can't ever go slack and loose. A string, on the other hand, if the tension in the string becomes 0, the string will go slack and there's no force left in the string. So we've got a light string OA of length 2 meters is fixed at O. It's free to move in the vertical plane about the point O. Particle of mass 0.4 kilograms is attached to A. Initially the particle is held with A immediately below O and is then given an impulse so that it initially moves horizontally to the right with speed u meters per second. And we've got to describe the subsequent motion of the system in each of the cases u equals 5, u equals 8 and u equals 10. Now in this case it's important to realise that there are 3 possibilities. We might get complete circular motion, that is, the particle goes round and round the circle without ever stopping and without the string ever going slack. Or we might get the swinging motion around the bottom of the circle as we had before, but now there's the third possibility that the string might go slack at some point, in which case the particle will then proceed by moving as a projectile because it's moving under gravity alone until the string goes slack and taut again. Now the analysis of this situation will start by applying the conservation of energy, and the details are exactly the same as they were in the case of the rod. So we'll pull that information across from the earlier consideration of the rod case. Now, with a string, we've got to investigate whether the string has the possibility of going slack or not. Does the tension in the string ever become 0? So what we need to do is start applying Newton's second law and use it to find an expression for the tension and then decide whether the tension could possibly become zero or not. So there's our conservation of energy equation. We need a new diagram now to become our force diagram so that we can apply Newton's second law. The force is acting on A, its weight, 0.4 G, and the tension in the string, OA. We know that there is an acceleration towards the centre of the circle of size v squared over r. And we also know that there is a tangential acceleration acting. It's a good idea to put this tangential acceleration onto the diagram, even though it's very unlikely that we'll need to use it in answering the question. So we're now going to apply Newton's second law towards the centre of the circle. So considering the resultant force towards the centre to begin with, clearly we've got T, and then we've also got to take the component of the weight towards the centre. Now we'll need to just do a little bit of trigonometry to get that. So we can see that the weight makes an angle of theta with the radius OA. So the component of the weight in the direction OA is going to be W cos theta away from the centre. So my resultant force is going to be T minus W, that's 0.4 G, times my cos theta. And the resultant force must equal the mass times the acceleration towards the centre, which is m times by v squared over r, but we know that m is 0.4 and r is 2, so that's going to be 0.4 times by v squared divided by 2. In other words, we've got T equals 0.4 G, that's 3.92, times by cos theta, plus 0.2 v squared. Now, if theta is an acute angle, cos theta is definitely positive, and that means that T must definitely be positive as well. So there is no chance that the string can go slack if theta is an angle between 0 and 90 degrees. Now, the conservation of energy equation gave me a useful expression for v squared, and we can insert that into our equation for t. So our equation for t now becomes t equals 3.92 cos theta plus 0.2 times by the expression for v squared, which is u squared minus 39.2 plus 39.2 cos theta. And if we tidy that up, we'll arrive at t equals 0.2 u squared minus 7.84 plus 11.76 cos theta. So we've got the expression for v at any point during the circular motion, and we can see that as theta increases from 0 to 180 degrees, v squared decreases. Well, conservation of energy would tell us that, but the equation is also telling us that. And we've also got t is 3.92 cos theta plus 0.2 v squared. And that was telling us that t cannot be 0 if theta is an acute angle. If t equals 0 when theta is an obtuse angle, then the 3.92 cos theta part of the t equation is negative, which means the 0.2 v squared part is definitely positive. So that tells us that for obtuse values of the angle theta, there is a very real possibility that t becomes 0 whilst the particle is still moving with speed v, which is non-zero. And finally, we've seen that we could rewrite the equation as t equals 0.2 u squared minus 7.84 plus 11.76 cos theta. So, there are three possibilities. First of all, we may have v equaling 0 for some acute angle, in which case we've got the particle swinging from theta equals alpha round to theta equals minus alpha and back again. Or there's a possibility that t equals 0 for some obtuse angle, and at that point there, if t equals 0, from then on the particle will be moving with an initial velocity of little v, whatever little v is at this particular point, and under the action of just the weight. In other words, we've got projectile motion until the string goes taut again. On the other hand, if t is never equal to 0, so if t is always positive for all possible values of theta, then the particle will go round and round the circle. So bearing these three possibilities in mind, let's consider what happens. First of all, if we have u equals 5, then we've got v squared is 39.2 cos theta minus 14.2. So if v equals 0, we've got cos theta equals 14.2 divided by 39.2, which gives me theta equals 68.8 degrees, and we have the particle swinging between 68.8 degrees and minus 68.8 degrees. Moving on to the case when u equals 8, then the v squared equation will now give us v squared is 24.8 plus 39.2 cos theta, which enables us to say that v equals 0 when cos theta is minus 24.8 divided by 39.2, in other words when theta equals 129.2 degrees. But we know that if we've got the particle stopping at an obtuse angle, there's a very real risk that the string may have gone slack before it ever gets to that point. So we need to look at the t equation, and the t equation is t equals 0.2 times u squared, so that's 0.2 times 8 squared, minus 7.84 plus 11.76 cos theta. In other words, I've got t equals 1.04 plus 11.76 cos theta. And from this we can see that t equals 0 when cos theta is minus 1.04 divided by 11.76. In other words, when theta is 95.1 degrees. So in this case, the particle will go round the circular path until theta equals 95.1 degrees, at which point the string goes slack and the particle will start moving as a projectile. And if we move on to the case when u equals 10, then the v squared equation becomes v squared equals 60.8 plus 39.2 cos theta. We know that the smallest possible value of cos theta is minus 1, which means that v is never going to equal 0 in this case, because the smallest possible value of v squared we've got is 60.8, take away 39.2, which is something around about 21.6. So v is never 0, the particle never comes to rest. What about the risk of t being 0? We need to check that out. So the t expression is t is 0.2 times 10 squared minus 7.84 plus 11.76 cos theta, which simplifies to t equals 12.16 plus 11.76 cos theta. And that is always going to be positive, because cos theta is always greater than or equal to -1. So T is always positive, which means the tension in the string never becomes 0. In other words, the string does not become slack. So the particle is going to go round the circle, make complete circles around the point O. Now at this stage we'll move on to our final example, in which we have a cylinder of radius 1.25 meters, is fixed in such a way that its axis is horizontal. We have a small particle P of mass 0.5 kilograms is initially held at a point A on the inside surface of the cylinder, which is at the same level as a point O on the axis. The particle is released with an initial downward velocity of 2 meters per second, so that it moves in a direction perpendicular to the cylinder's axis. At a later time, the particle is still on the inside surface of the cylinder with angle AOP equals theta, and the particle is moving with speed v. So here we are, we've got the initial diagram, and we have the diagram a little while later, while the particle is still on the surface. And we have to obtain an expression for v squared in terms of theta, we have to find the reaction, and we have to describe the subsequent motion of the particle. So, here's our initial diagram, here's the new diagram, and if we're going to get the v squared expression, we're going to have to, as usual, start by getting the conservation of energy. And in this case, as it moves from the initial position to the general position, we're losing potential energy and gaining kinetic energy. So we can apply the conservation of energy as loss in potential energy equals the gain in kinetic energy. The loss of the potential energy is going to be 0.5, the mass, times by g times by h, and that is going to equal the gain in the kinetic energy, which is the final kinetic energy, a half, times by 0.5 times by v squared, minus the initial kinetic energy, a half times 0.5 times 2 squared. Multiplying up by 4, this gives us 2gh equals v squared minus 4. But a little bit of elementary trigonometry on the green triangle in the second diagram gives me h equals 1.25 sine theta. So 2 times 9.8 times 1.25 is 24.5 sine theta equals v squared minus 4. In other words, we've got v squared equals 4 plus 24.5 sine theta. To find the reaction between the particle and the cylinder, we're going to need to use Newton's second law, which means that we need a force diagram for the setup. The forces acting on P are the weight, 0.5 g, and the reaction force R. We also need to show the acceleration of v squared divided by the radius acting towards the centre of the circle, and as before, it's not a bad idea just to show the tangential acceleration there as well. Now we're going to apply Newton's second law radially to find our expression for the reaction force R. And in order to do that, we're going to need to know what the component of the weight is in the radial direction. So, this needs just a little bit of chasing around with angles. So if we first of all extend the radial line a little bit and form a right angle triangle with this radial line and the weight, And we'll put on a parallel line to the horizontal line. Then alternate angles tells me this angle is theta. The right angle between the horizontal and the vertical tells me I've got 90 degrees there. So the angle between the weight and the extended radial line is going to be 90 minus theta, using angles on a straight line. We've got a right angle in the red triangle, and the final angle in the red triangle must therefore be theta as well. We want the radial component of the weight, which is the side opposite the angle theta in the red triangle. So the component is going to be W sine theta, or 0.5 G sine theta, and this is acting away from the centre. So now, applying Newton's second law radially towards the centre of the circle, we have got R minus 0.5 G sine theta is the resultant force, must equal a mass 0.5 times by v squared divided by the radius of the motion, so that's 0.5 times by v squared divided by 1.25. So we've got the reaction is 4.9 sine theta plus 0.4 v squared. We know that v squared is 4 plus 24.5 sine theta. So we've now got R is 4.9 sine theta plus 0.4 times by 4 plus 24.5 sine theta, which gives me 1.6 plus 14.7 sine theta, which is the required expression for R. So finally, we've got to describe what happens to the particle. So we've got v squared is 4 plus 24.5 sine theta. We've got R equals 1.6 plus 14.7 sine theta. Clearly the particle has got sufficient energy to reach B, and that up to that point, for angles of theta which are between 0 and 180, R is certainly positive. Beyond B, it's possible that R may be 0 and the particle will leave the surface. So let's have a look at see whether that happens or not. For R to equal 0, we've got 1.6 plus 14.7 sine theta must equal 0. In other words, sine theta must be minus 1.6 divided by 14.7. Now that will give me either theta equals minus 6.25 degrees or minus 6.249 degrees, or theta equals 186.249 degrees. We know the particle will certainly get up to the theta equals 180 point, so it's clear that we want the 186.249 degrees result. So we've got R equals 0 when theta equals 186.2 degrees. So the particle moves around the cylinder until theta equals 186.2 degrees, at which point R becomes 0, and at that point the particle is going to lose contact with the surface of the cylinder and will move under the action of gravity alone, so it will become a projectile again. And that concludes our look at motion in a vertical circle.